Good morning, everyone. Today we will be continuing our discussion on the general properties of elements of a periodic table. So here today we will be discussing on melting point and boiling point. So when we started the class last week, we tried to find out what do you mean by we tried I tried to ask you some questions like what do you mean by like what is the basis behind the deciding factor of the melting and boiling point, and some of you told me that the basis for the trends that we observe in the melting and the boiling point was metallic bond, right? Metallic bonding was the thing that you suggested. So at that time, I told you that no, we have another terminology that is the deciding factor, and that is the cohesive energy. Okay, so uh, when I went back and looked into more in detail about this cohesive energy, I found that this cohesive energy has, to some degree, uh, like influence from all different types of bonding. So, if you talk about the different types of bonding that you find in elements, you will have metallic bonding, you will have in ionic solids ionic bonding, you will have covalent bonding, you have van der Waal, hydrogen bonding. So various different kinds of bonding you will find in various solids. So, and we cannot say, like for metals, we cannot say that there is 100% metallic bonding only and no other type of bonding. So there is a collective influence of all different types of bonding and other type of interaction that are all resulting in the formation of a particular crystal structure. So that is why uh, basing it completely on one particular factor that is more influential in case of metal elements, that is metallic bonding, won't be a kind of conclusive factor which can influence the melting and boiling point of the rest of the elements of the periodic table. So in taking into consideration all those facts, it is better to use a term called cohesive energy. Now, how do you define cohesive energy? It is the energy released on account of the formation of elemental crystal from elements in its gaseous state. So, this particular crystal, when you heat it and when you convert it into M gas, that means you convert this crystal completely into atomic state where M all are atoms. Okay, so this is called the heat of atomization, which is represented by delta H. Now, cohesive energy is having a equivalent value to this, like in terms of numerical value, it's equivalent to heat of atomization, but with a opposite sign. Okay, so here heat of atomization, it's an endothermic process. However, the reverse of this process would be a exothermic process. So that reverse process from an atomic state to a crystal state, what is the energy release? That is what is termed as the cohesive energy. So that's what here I have told, that cohesive energy is equivalent to heat of atomization but with an opposite sign. Now, if you look into the trends of the cohesive energy, you find that it decreases down the group, and thus it is kind of inversely proportional to the internuclear distance. So this we can understand because as we move down the group, what happens? The covalent radii or the ionic radii keep increasing. So as a result, what happens? The internuclear spacing between the two atoms would increase. So that can be considered as a reason for why there is a decrease as we move down the group. Then across the period, it increases, like the cohesive energy increases across the period owing to the dependence on valency electrons, that is the number of electrons that are available for bonding, increases as you move from the left to the right of a periodic table. So that is why across the period the cohesive energy increases. Down the group it decreases, across the period it increases. This is a general trend that you find when we discuss about cohesive energy. Now let us look into this particular cohesive energy in little bit more detail. Cohesive energy depends upon two important rules. Like two important factors decide on the strength of the cohesive energy, okay, or the magnitude of the cohesive energy. One of the factor is the number of unpaired electron available for bonding. Okay, so uh, for bonding to happen, the electrons in the valence shell should be unpaired. Only then it would be of any use for for doing any type of bonding. So if you take the first group, its electronic configuration is NS1. Okay, NS1 means it has one unpaired electron for bonding. Now let us take group 2. If you take group 2, it has an electronic configuration of NS2. Okay, so if you see NS2, you will say that it is paired, so there is no unpaired electron. So why the cohesive energy is higher? This is because what happens is that if I just use and then I'll show you. So in case of group 2, the electronic configuration was NS2. Okay, so this is the ground state electronic configuration of the NS, the group 2. So what happens is that when you kind of excite these atoms, the electrons, the paired electron would be excited to its next NP state. Okay, so now you have how many unpaired electrons available? There are approximately how many? Two unpaired electrons available in the case of group 2. Now if you take the group 13 element, the electronic configuration is Ns2 Np1 in the ground state. Now when you talk about the excited state, the paired s electron will excite it to the p. So the electronic configuration now would be Ns1 Np2. So there are three unpaired electrons available when it comes to the group 13 elements. However, in the same way, when you go to the group 14 element, there are four unpaired electrons available. So as you move from left to right in the periodic table, what you see, the number of unpaired electrons that are available for bonding increases, and that is why you see an increase in cohesive energy when you move across the period. Okay. Now, if there is another factor on which it depends on, and that is the type of the crystal. Okay, so depending upon the number of electrons in the s and p orbital, or the number of s and p orbitals available for bonding, decides the crystal structure that is being formed. I have shown a table in the next slide. You will see that when the number of s and p subshell that is participating in the bonding is less than 1.5, the structure that is formed is body center. So in case of group 1, we came to know that how many subshells are how many electrons are bonding. There are only one s electron that is involved in bonding, so it is less than 1.5. so that is why most of the group 1 element, they have a crystal structure in which the arrangement is body centered kind, body centered cubic. Now, when the pairing or the number of s and p electron atoms fall in the range of 1.7 to 2.1, you will see a HCP, that is hexagonal close packing. Similarly, 2.5, 3.2, you will see a cubic close packing, and when it is nearing to 4, you will see a diamond kind of crystal structure. That is what you find in the case of group 14 element. Now in group 2, the number of unpaired electrons are the s and p electrons. If we consider the excited state is 2, so it will fall in this particular range. So they should exhibit a hexagonal close packing. Okay, so similar in this way, it is a kind of general thing, but you will see a lot of exceptions, which we'll be discussing some of the exceptions in this particular session. Okay, so let's look at the individual groups now. Now we have to study 4 different groups in this module. So group 2, group 1, 2, 13 and 14. So I have written down their corresponding melting point trends and the boiling point trends I have written down here. So if you look in here, let's start with the group 1. So if you look at the group 1, what do you see? You see a very smooth trend in the smooth decrease in the melting point as you move down the group. Even the boiling point also shows a similar trend. So why that is so? Because there is a smooth increase in the covalent radii. Okay, so when the covalent radii increases, the internuclear distance increases, so cohesive energy kind of reduces. Okay, so that is one reason why you see a very smooth decrease in the melting point as you move down the group, because there is a smooth decrease in the uh, in the in the cohesive energy as you move down the group in the case of group 1. Now when we move to group 2, that is the configuration is ns2. So here there is a kind of irregularity that you find in here. So what do you see here? In the case of the beryllium, the melting point is this, and it reduces in the case of magnesium to show 649. So beryllium magnesium forms a BCC as predicted in the previous. So as predicted, it is showing a structure of BCC. But when it comes to the calcium, you see a significant increase in the kind of structure in the melting point. Now, why that is so? That is because in case of calcium and strontium, the crystal structure is changed from the BCC to a CCP kind of structure. Now, why this change is happening? The reason is kind of unknown here, but because of this change from the HCP to a CCP structure, you will see that the melting point increases. Because if you compare the crystal structure or the arrangement of atoms in the HCP and CCP, the CCP close packing is kind of more compact close packing. So there you will see more cohesive energy because of the compact close packing that you see in CCP kind of crystal arrangements. Okay, so please correct this. This is not BCC, this is HCP. BCC we will find in group 1 where the number of s electrons is less than 1.5. So because it is group 2, it is more, it's the second case where the structure is HCP, not BCC. Okay, so please correct this. This is not BCC, but it's let me correct it here itself. It's HCP, that is hexagonal close packing. So what happens? Why there is a change here? You observe it is usually decreasing. The usual crystal arrangement should be HCP, that is hexagonal close packing. So as you move down the group, it should decrease, and from beryllium to magnesium, it is decreasing. But suddenly you see an increase in melting point, and that increase is because of the change in crystal structure from HCP to a CCP arrangement. And CCP arrangement is more compact arrangement, and more cohesive energy you will find in CCP arrangement. And that's why you see a sudden increase when it comes to calcium. Okay, so that is how you see. Another observation that you can make in terms of crystal structure is that barium in ideal it should form a HCP, right? HCP structure is what you will expect for a group 2 element, but barium forms a body centered kind of arrangement. Now body centered can be formed only when the number of S or P electrons is less than 1.5. Now how come that is possible here? If it is possible only when this one of the electron in the excited state goes to the D subshell. Rather than going to the P, it will go to the D subshell. So now how many electrons are remaining in the S and P? Only one electron would be available. So in that case, the barium can form a BCC kind of arrangement. So this is what the explanation given for why barium acquires a body-centered structure. Okay. Now let us move further to the group 13 element. So in group 13 element, what you find is that there is an unusual increase in the melting point in the case of boron, and there is an unusual decrease in the melting point when it comes to gallium. Now we have to find out why that is so. And in both these deviations, what is important to know is that it is coming as a result of the unusual crystal structure of these elements. Okay, so boron, as you know, that borons are a little bit electron deficient in structure. They try to combine themselves in such a way that they form a kind of geometric structure called icosahedron units. Okay, so if you look at these icosahedron units, these looks like this geometry. Each of the green balls represent the boron atom. So there are 12 boron atom in this icosahedron unit. Okay, 12 boron atom in this icosahedron unit, and there are approximately 20 phases on this icosahedron unit. And these icosahedron units are arranged in different fashion, giving to 4 different allotropic forms of boron crystal. Okay, so one of the simplest crystal structure of boron is alpha rhombohedral boron. Okay, so that is the most simplest one. Even in that kind of arrangement, it is not reaching to an complete close CCP kind of packing, because the amount of gap, it is not an efficient packing as you would expect of a CCP kind of packing, because as I told you, these elements would show theoretically should form a CCP kind of packing because availability of the 3 unpaired electrons. But boron being little bit electron deficient and having a high ionization energy, they prefer to form these B12 icosahedron units, which are arranged in different ways, giving rise to 4 allotropic forms. And the simplest one is the alpha rhombohedral form. And they are not efficient as CCP, but still they are kind of arranged in such a way that it gives a kind of little bit more compact way of arrangement, that it leads to an unusual high melting point in the case of boron. Now, when it comes to gallium, why there is this great reduction in the melting point is because in gallium, if you see in the crystal structure, if you see the intermolecular distance, interatomic distance, you will find that 2 of the gallium will be having each of the gallium is surrounded by other gallium atoms, right? So one of the gallium atom would be having like the internuclear distance would be 2.43 Armstrong, and the rest of the nearby gallium atom, they would all be having approximate internuclear distance of 2.70 Armstrong and 2.79 Armstrong. So they are far away. So most of the time what you will find is that there would be kind of this kind of diatomic way in which the crystal is arranged. So you will find that discrete diatomic gallium ion is spread throughout the gallium crystal. Okay, so that is why this particular crystal structure doesn't have a very kind of good packing. because it is not it is like two atoms together and they are spread over the whole crystal structure, so that you can expect that there is no much cohesiveness between all the gallium atoms. It's like two diatomic or gallium being spread throughout the crystal, so you can expect that the definitely the cohesive energy would be a little bit less. So that is why here, in the case of helium, the liquid expands when it forms a solid. So, solid is less dense when it comes to liquid, because here, as I told you, the Y density is less because the gallium atoms are far away from each other. Only you will find two gallium atom would be having internuclear separation of 2.43, but rest of the gallium would be higher internuclear separation. It is like 2.70 and 2.79. So you will see, when you see the gallium atoms in a gallium crystal, you will find diatomic gallium being spread throughout the crystal structure. So that is why you have less density of the solid than the liquid in case of gallium, and this you will find also in the germanium and the bismuth elements as well. So that is why you see a marginal change in the uh, in the in the melting point in the case of helium. Our boiling point is pretty like a uniform decrease you will find in the case of group 13 elements. So whatever change is happening here in the melting point is only because of the unusual crystal structure that these elements adopt. Okay. Now let us go to the 14th element. So 14th element, what you find is that if you see the trend, there is a kind of decrease happening as you move down the group. But still, what you find here is that there is a kind of pretty high melting point you observe in the case of silicon and germanium. That is because the silicon and germanium form a similar crystal structure to that of carbon, and that is diamond crystal structures. And diamond crystal structure, because they involve covalent bonding, they are pretty strong, and that is why you see comparatively higher melting points in the case of silicon and germanium. However, when it comes to tin and the lead, what you find is that there is a sudden decrease in the melting point, and this can be understood in this way, that they are not using all the four electrons which are available for bonding in here, and that is because you can know it is because of inert pair effect, because inert pair effect keeps the ns electron reluctant to participate in any kind of bonding. So whatever bonding is coming is from the np2 electrons. So since only two electrons are participating in kind of bonding, they have little bit weaker cohesive energy as compared to the rest of the elements of the group 14 elements. So that is why you see a sudden decrease in the melting point in the case of tin and the lead structures. So I hope I made these points pretty clear to every one of you. You please go through these trends, and what I would like to, I've given you a brief hint about all the trends. Now what I would like you to do is just to concentrate on whatever I have discussed, and you would definitely would be having a lot of confusion, a lot of doubts. So that I would like you to ask during the live session, and then we will build our discussion on that basis. Thank you very much for your patient listening.